Hello and welcome back to Statistics. It's Monika Wahi, your Library College lecturer, and you've made it to Chapter 7. I broke up Chapter 7 into bite-sized pieces, and we're going to start with Chapter 7.1, talking about the normal distribution and the empirical rule. So here are your learning objectives for this lecture. At the end of this lecture, you should be able to state two properties of the normal curve, state two differences between Chebyshev intervals and the empirical rule, and explain how to apply the empirical rule to a normal distribution. So remember distributions. We learned about them a while back, but I'll remind you a little bit about them. And then we're going to talk about properties of the normal distribution, or specifically the normal curve, that shape that comes out of making a histogram of normally distributed data. Then we're going to remember Chebyshev intervals. We're going to talk about what Chebyshev did for us and what Chebyshev really didn't do for us. And then we're going to move on to the empirical rule, which works very well, better than Chebyshev intervals when you have normally distributed data. And then I'm going to show you an example of how to apply the empirical rule to that normally distributed data. So remember the normal distribution. In fact, remember distributions at all, right? So to get a distribution, and a lot of people sort of forget this by the time we get to chapter 7, but I just wanted to remind you. This was from an earlier lecture. We had a quantitative variable, which was how far patients had been transported. And we determined classes, and we made a frequency table. So remember that? And then after that, we made a frequency histogram, and it made a shape. And as you could see, that shape, which is the distribution, that shape in this one was skewed right. See that light on the right? Okay, but that's an example of something we cannot apply the empirical rule to, because the empirical rule only applies to normally distributed data. So I had to give you an example of that. And here's my example. So when I was in my undergraduate in costume design at the University of Minnesota, they made us take a chemistry class in one of those big lecture halls. So I was in a very large class that probably had about 100 people. And we were given this really difficult test. It was a 100-point test, and I was used to getting like A's. And so when they were done with the test, the TAs were handing the tests back to everybody so they could see their grade, while the professor was writing on the board and was writing the frequency of all the different scores. And I remember the TA handed me my test and it said 73 on it. And I'm used to getting like 90s up to 100. And I remember stating out loud saying, 73, that is an awful score. I can't believe I did so badly. I was talking like that, but at the same time, the professor was writing the frequencies on the board. And what I realized is the top score was in the 80s. And I had the third top score, was 73. That's how hard the test was. And that's when I shut up, because I noticed everybody giving me dirty looks because they had scored actually below me. So I wanted you to imagine that class, and I imagined what the normal distribution would look like for that class with the distribution of the scores. And the reason why I thought it would be normal is because we all did badly, right? And so nobody got 100, so we were all below the 100. So I imagined this curve here for you, and I imagined my class had 100 people just to make it easy. Of course, the test was difficult, and nobody got 100 points. And the mode, the median, and the mean were all near a C grade, because you remember how when you have a normal distribution, the mode, median, and mean are all on top of each other. So we all did pretty badly. So I'm going to use this example of the fake chemistry test scores to exemplify these properties of the normal curve. So there's 5 I'm going to talk about. The first is that the curve is bell-shaped with the highest point over the mean. And so you can see I drew a scribbly little curve, put a little arrow there to show you that that's where the mean of the scores were. And then I also wanted you to notice that the curve is symmetrical with a vertical line through the mean. So there's like a mirror image of the curve on either side. Now it's not perfect, obviously, but it should be roughly like that. And you know this is not true of skewed or bimodal or these other things we've been talking about. Okay, and the third property is that the curve approaches the horizontal axis but never touches it. You don't have to memorize this, but remember asymptote or asymptotically close? That's when a line gets really close to another line, but they never touch. It's so romantic. But anyway, that's a very Bollywood thing to say, by the way. But so the curve approaches the horizontal axis and never touches or crosses it. Um, then also there's this inflection or these transition points between cupping upward and downward. And these transition points occur at about the mean plus one standard deviation and about the mean minus one standard deviation. And this is a little hard to explain, but imagine you're on a roller coaster and you're going up this normal curve. There's this part where you're just mainly going up. Well, the part where it seems to kind of level out and you're at the top of the curve, you start sort of relaxing. That's that inflection point. And so as you're going over in your roller coaster and you're in that flat part, and then you start kind of going down, that's the second inflection. So that's where what it's saying about is the property of this curve is that you have these inflection points like that, and they roughly occur at plus or minus one standard deviation above and below the mean. Then finally, and I colored this in just so you could see it, the area under the entire curve is 1. So think 100%. So it would be nice if that were a square or a rectangle or even a triangle, something that we're used to in geometry, but it's not. It's this goofy shape, right? But still, you need to get it in your head that that shape is worth 1.0 in proportion land or 100% in percent land. And what I mean by that is, let's say we cut that shape in half. The each side would have 50% or zero point 0.5 on it. Then let's cut it a different way. So the part of the curve on the right side of that line is a fourth of the curve or 25% of the curve, even though it's goofy shaped. And the part on the left side is 75%. So that's what we're trying to get you to think like, is that, yeah, you can just declare that all the area under the curve equals 1 or 100%. But the reason why we're declaring that is because we're going to cut it up and say different amounts of percents of the curve. Now we get to the empirical rule, since we reviewed this whole curve thing. And I'm going to make you remember Chebyshev, I'm sorry. But, let's talk about Chebyshev. Chebyshev helped us get some intervals, right? And intervals have boundaries or limits. They have a lower limit and an upper limit. That's how you know what bounds the interval. So when we were doing Chebyshev intervals, what we would do is we'd figure out a lower limit and upper limit, and we'd say at least so much percent of the data falls in the interval, right? So when we would choose a lower limit of mu minus 2 times the standard deviation, and the upper limit was mu plus 2 times the standard deviation, we would say at least 75% of the data were in the interval. So I wanted to just show you a demonstration using my fake class. So remember there were 100 students in the class. I actually came up with a mu for them, and their mu on the test was 65.5. So my 73 was better than the mean, but not much better, right? So the mu for that class was 65.5 and the standard deviation was 14.5. So I calculated this Chebyshev interval for 75% of the data. So I took 65.5 minus 2 times 14.5 and I got 36.5, which is a pretty bad grade. And then the upper limit was pretty good, right? 65.5 plus 2 times 14.5 equals 94.5 on a 100-point test. That's a pretty good grade, right? So if you had 100 data points or 100 students, at least 75 would have scored between 36.5 and 94.5. So you're probably already realizing, okay, that doesn't really help Monika, who scored 73. And this is a really wide range. We say at least 75% of people scored there. You could have probably guessed that without even knowing about Chebyshev intervals, right? So it didn't really help me narrow down like how well is this class doing. If I had had the mu and the standard deviation, I could have calculated this and said, okay, I'm no better off. So Chebyshev's theorem on the left side, it applies to any distribution. You don't need a normal distribution. You can use that skewed distribution. Also, you'll notice it says at least. So like this was at least 75% of the data fell in there. Maybe even 100% fell in there. So it doesn't really help us. And as you go, you start with 2 standard deviations. If you go out 3, it's 88.9%, and 4, it's 93.8%. You might as well start at the beginning and say almost 100% of the data falls in this interval. And if you're saying that, it's not very useful, right? But it kind of gets stuck doing that because Chebyshev's theorem applies to any distribution. The empirical rule is much more elite. It only applies to the normal distribution. And you'll see why, if you are lucky enough to get a normal distribution, that you want to use the empirical rule instead of Chebyshev, okay? Because secondly, the empirical rule says approximately. It doesn't say at least. So it's saying basically not at least. It's saying about exactly this. So you can trust it. Okay, you don't have like this unknown, like maybe 100% is in there. So it says, this is what it says, and I'll show you a diagram of it, but it says that 68% of the data are in the interval mu plus or minus 1 standard deviation. So mu minus 1 standard deviation all the way up to mu plus 1 standard deviation. 68% of the data are in there. And you'll notice that Chebyshev didn't even say anything about 1 standard deviation. And so already we've got something way more useful if we apply the empirical rule, right? So next we go to 95% of the data are in the interval mu plus or minus 2 standard deviations. 95%, approximately 95% are in there. Now, if we had bought Chebyshev, we'd be saying about this too, we'd be saying 75%. Okay, we'd be saying at least to 75%, which could be 95%. But here, if we're using the empirical rule, we're relatively sure that it's 95% between mu plus or minus 2 standard deviations. You can like bet on it, right? Finally, if you get out to 3 standard deviations, you're kind of running out of data because 99.7%, almost all of them, fall in that interval. So as you can see, the empirical rule is going to give you a more specific answer. But again, you can only use it if you have a normal distribution, but which we do. So let's go look at that. Okay, this is a diagram that I'm going to help. I made it myself actually because I thought it was the other diagrams I saw were not pretty. And this one is very pretty in my mind. But let me unpack this diagram for you because there's a lot going on in it. First of all, I want you to notice the shape of it. It's a normal distribution, okay? And then I want you to notice that I put this black line down the middle and I put a little arrow that says mu. So this is where we want to imagine mu is, no matter what your actual numbers are for mu. Like in our case, this is 65.5 for our points. Just imagine whatever your mu is and whatever your standard deviation is, this is where you would put the mu, right? Then you'll notice that each of these sections that's colored has a little standard deviation symbol in it because that's representing that the width of that is 1 standard deviation. So if your standard deviation was like 5, then mu would be plus or minus 5. Like the green one would be mu plus 1 standard deviation, so it would be mu plus 5. And then you draw that parallel line there and see that arrow that says mu plus 1 standard deviation, that would be there. And of course I just had to use these symbols because I don't know how big the standard deviation really would be or what the mu really would be. But whatever it was, mu plus 1 standard deviation, if you go up there, you would see that that green area represents 34% of the data. And if you're lucky enough to have exactly 100 people like I did in my demonstration, that would mean that between mu and mu plus 1 standard deviation of these test scores would be 34 people's scores, right? So you could really figure that out. Same with the yellow section, only that's mu minus 1 standard deviation, and 34% of the scores would be between those two numbers. Now you'll see as you get up into the blue, that's between 1 and 2 standard deviations above the mu. You'll see that because the roller coaster is a lot lower to the ground there, that section is really small. It's only 13.5% of the data. And the same with the orange one. That's on the other side of the mu, so that's below the mu. And that's only 13.5. And then you'll notice that at 3 standard deviations, between 2 and 3, there's a little tiny piece, right? The purple piece and the red piece, those are only worth 2.35% of this shape. And then I wanted to point out there is some stuff at the end in the little black part beyond 3 standard deviations on either side. There's 0.15%. And a lot of times people forget that. But one way you can make sure that you got to remember that it's there is that if you add up all these percents on the slide, you'll get 100% because remember I promised you that the whole curve is worth 100%, and this is how we split it up. I also want you to notice that there's kind of a cheat, right? If you just add up the green, blue, purple, and then the little black part at the end, if you just add up those percents, you'll get 50%, right? Because it's half the curve. And the same, you'll get the same thing if you do the yellow, orange, red, and the little part and the black at the bottom. If you add those up, you'll get 50% too. So that's how you want to just conceptualize this whole empirical rule diagram. But now we'll apply. So I put the empirical rule diagram on the left, and then I put our class frequency histogram on the right. And look, I put the mu and I put the standard deviation so we could have it there. Now the first part of this section, I'm just going to show you how to fill in the numbers under the diagram. Okay? And then after we fill in the numbers, I'm going to talk to you about how to interpret those numbers. So let's start with easy. Let's write the mu underneath the symbol for mu, which was 65.5. So we just wrote it. That was simple. Okay? Now let's do the plus or minus 1 standard deviation. So you'll see 65.5, which is our mu, minus, and I put 1 times 14.5. I know, I just did that for demonstration purposes. So you see we're doing 1 times the standard deviation. So if you subtract that from the mu, you get 51. And so I wrote that 51 underneath the mu minus 1 standard deviation. And if you go the opposite way and you add on 14.5, you get 80. So I put that up there. So I just labeled those two. You can kind of guess what we're going to do on the next slide. Surprise! We're going to do almost the same thing. Oh, we're doing the mu minus 2 times the standard deviation to get the 36.5, and the mu plus 2 times the standard deviation to get that 94.5. And you probably already were ahead of me with this one. This is where we do 65.5, the mu, minus 3 standard deviations, and we get 22. And then we add 3 standard deviations, and we get 109. And now we're all labeled. So what does this all mean? Well, remember our n equaled 100, just out of convenience. So what does this mean? It means that 34% of the scores are between 51 and 65.5. So that's the yellow bar, right? So 34 scores were that because I had 100 people in the class. So I'm standing there in that class and I've got a 73. But I know 34 of those people I'm looking at have a score between 51 and 65.5. I also know that another 34%, or another 34 in this class because there's 100, have a score between 65.5 and 80. And my 73 is somewhere in there, right? So already I'm getting an idea that 68 people, or 68% of the scores are going to be between 51 and 80, right? And so I'm right there with 68% of the class. So I'm going to go through some fake test questions for you to just show you how to come up with the answer. So let's say the question was, what percent of the data student scores are between 36.5 and 80? So think about how you would answer that question. So see where 36.5 is? It's on the lower limit of the orange part. And see where the 80 is? It's on the upper limit of the green part. So what you would do is you would add up the percents in between, right? 13.5 plus 34 plus 34. And the answer to what percent of the data are between 36.5 and 80, the answer would be 81.5%. Here's another question. What cut point marks the top 16% of the scores? So already you know you're up in that area, probably where the purple or the blue are, right? And so what would make the top 16%? Well, if you actually add together that 0.15% from the little black part, the 2.35% from the purple, and the blue 13.5%, you'll get 16%. So the cut point then for that, all the scores above 80, that would constitute the top 16% of the scores. Here's another quiz question. What percent of the scores are below 94.5? So we see 94.5 is at the upper limit of the blue section. So you could kind of say, well, let's just add up everything below it, right? We'll add up everything below it, and that percent of scores will be below 94.5. And so we do that. We add up everything below it. But remember how I said that the yellow, orange, red, and the little black part there, that equals 50%? If you just wanted to say, okay, that's 50% plus the green part plus the blue part, you could do that and you'd get the same answer. So what are the cut points for the middle 68% of the data? I just wanted to show you an example of what if they say middle, right? Well, you're going to have to be centered around mu then, right? So the middle 68% means 34% above the mean and 34% below the mean. So the cut points would be 51 to 80. Okay, now I'm going to ask a similar question, but I'm going to use different words. Okay, what is the probability that if I select one student from this class, that student will have a score less than 80? Okay, so notice I'm using totally different terminology. I'm saying what is the probability? Yet the actual answer is what you would probably guess, which is where you add up all the percents below 80. So the point of me giving you this quiz question is to point out that percent and probability mean the same thing when you talk. So either I'm going to say what percent of the data are below 80, the score of 80, or what is the probability that if I select one student, that student will have a score less than 80. That is actually the same question. So the answer is going to be, I use that 50% trick here. That answer is going to be 50%, which is the whole bottom half of that curve, plus 34% gets up to 84%, right? So the probability that if I select one student, that student will have a score less than 80 is 84%. And that's the same as what percent of the data is below 80 is 84%. Okay, here's another probability question. What is the probability I will select a student with a score between 36.5 and 51? Well, that's as if I was asking, it's the same question as what percent of the data are between 36.5 and 51, which you would know the answer to that. That would be 13.5. That's the orange part, right? But even if I say, what is the probability I will select a student with a score between 36.5 and 51? It's 13.5%. So let's say that we were at a casino and we were betting, right? And I'm like saying, okay, there's 100 students. I'm going to just grab a score out and I'm betting a lot of money that I'm going to grab somebody between 36.5 and 51. And you'd probably be like, you don't want to bet on that because you only have a 13.5% probability of selecting one. You probably want to bet, if you're going to bet, on something in the yellow section or something in the green section because they have higher probability. So that's how you would think about probability and percent, even though they're kind of the same thing. I just wanted to show you how they word the questions differently, but it means the same thing. So now I want you to just sit back and think for a second. So think about what would happen in a different class taking the same hard test, meaning nobody's getting 100%. What if the mu was the same, meaning everybody's doing badly, but the standard deviation was larger than 14.5? What would that do to the intervals? So let's just stare at this for a second. Let's say the mu was still 65.5, but the standard deviation was like 30. Okay, that there was a lot of variation in the class. That would already mean that where the 80 is right now, that would actually be 95.5, right? And where that 51 is there now, if we had a standard deviation of 30, that would actually be 35.5. I mean, that'd be a way bigger interval, right? And so the class I was in chemistry was an undergraduate class. I was in costume design. This was a whole bunch of different kinds of people in chemistry. And that's probably why we even had kind of a big standard deviation of 14.5, even though I made that up. I mean, in reality, we probably did have a big standard deviation. I knew in the chemical engineering department, they had chemistry classes for chemical engineering majors. I'll tell you, their standard deviation was probably a lot smaller because they were probably more alike and got more similar grades as each other. But with this diverse class, we probably had a pretty big standard deviation. So that gets to my last question. What if the standard deviation was actually smaller than 14.5? So if we were like in the chemical engineering class and they were taking chemistry and they had a smaller standard deviation, maybe they might have had the same mean, 65.5. But let's say their standard deviation was like 5. Then where the 80 is now would be is 70.5. And where the 51 is would be a 60.5. And we'd have way more confidence of where we knew the scores fell. Like as I was standing there with my 73, um, I would be saying like, oh, my 73 is pretty high if everybody has a small standard deviation, right? Whereas it's not that high here because we had kind of a big standard deviation. It's in the first, the green part. So the reason why I wanted you to think about that is that's why this shape goes by mu and standard deviation because it really matters how big the standard deviation is, how big each of those areas are with the different colors. So I just wanted to remind you that percent, area, and probability are all related. The percents literally refer to the percent of the area of the shape, okay? And imagine the whole thing is 100%. So just to remind you, the orange part is 13.5% of the area of the whole shape, but it also is the probability that an x, like a student, an x, falls between mu minus 1 standard deviations and mu minus 2 standard deviations. And that if I select one x from this group, that 13.5% is the probability that I will get an x in that range. And so it means both things. So in conclusion, the empirical rule helps establish intervals that apply to normally distributed data, and it's more useful than Chebyshev because it's more specific. These intervals have a certain percentage of the data points in them, and they also refer to the probability of selecting an x in that interval. And these intervals depend on the mean and the standard deviation of the data distribution. So if those change, then exactly where the numbers are on those intervals change. Well, I hope you enjoyed my explanation of the empirical rule, and now you can practice doing it yourself at home. Good morning, good day, and good afternoon. This is Monika Wahi, your Library College lecturer, here moving you through chapters 7.2 and 7.3, z-scores and probabilities. I decided to mush these two chapters together because I thought they actually kind of belong together. I didn't really understand why they were separated. So at the end of this lecture, you should be able to explain how to convert an x to a z-score, show how to look up a z-score in a z-table, explain how to find the probability of an x falling between two values on a normal distribution, describe how to use the z-table to look up a z corresponding to a percentage, and describe how to use the formula to calculate x from a z-score. Well, that sounds like a lot, but you'll understand it at the end of this lecture. First, I'm going to go over what a z-score is and what the standard normal distribution is. Then I'm going to talk about z-score probabilities and what those are. I'm going to show you how to use the z-table to answer some harder questions besides the ones I talk about during the z-score probabilities section. Then I'm going to show you how to use a slightly different formula to calculate x from z. Finally, I'm going to just remind you some tips and tricks about using z-scores and probabilities correctly. So all this talk about z-scores. So what is a z-score and what is the standard normal distribution? Well, let's take a look at this very pretty thing I made. You may recognize it from the last lecture. It was my little empirical rule diagram. So remember the empirical rule. Remember how it required a normal distribution. Well, that worked well for the cut points available, right? Like mu plus or minus 1 standard deviation, mu plus or minus 2 standard deviations. If we asked questions that were right on those cut points, we had good answers. But what about in between those cut points? So I wanted you to notice in this empirical rule diagram these numbers at the bottom. Like I just circled them, like -3, -2, -1, and then mu doesn't have a number, so pretend there's a 0 there. And then there's 1, 2, and 3, okay? That is the standard normal distribution, and that is also called z. So these things on the right, those are z-scores. So see the green area? 0 is the z-score that's on the lower limit of that, and 1 is the z-score at the upper limit of the green area. So you can see that this whole curve, the standard normal distribution on the right, the mu of the whole curve is 0, and the standard deviation of the whole curve is 1, and that is what z-score is. So I just want you to notice the concept of standard. I'm in the US, and in the US we use, the US dollar. But one of the things I've noticed is that a lot of countries see it as a standard. So they'll map their currency to the US dollar. So maybe the euro will map its currency to the US dollar. Maybe the Egyptian pound will also map its currency to the US dollar. And once it does that, it's a lot easier to compare them, right? And so that's the main reason for the standard normal distribution is it helps you compare x's from different distributions, different normal distributions that have different mu's and different standard deviations from each other. It helps you map them to this normal, standard normal distribution here that's standard so you can compare them. So let's talk about z-scores. Every value on a normal distribution, so every x, can be converted to a z-score. Just like I was saying how you can convert any currency to dollars. There's some formula for that. So you can convert every x on a normal distribution to a z-score, but you have to know how to use the formula, right? And what goes into that formula? Well, first you need the x that you want to convert to a z-score, so you need to pick one. Then you need to know the mu of your distribution, your normal distribution, and the standard deviation of your distribution. And here are the two formulas that are used. The one I was just talking about is on the left, is the formula for calculating the z-score. And we'll go over the one on the right later in this lecture. So remember in the last lecture, I was talking about a class that had 100 people in it and that all took a really hard test. It was so hard nobody got 100%. And it was a 100-point test, so nobody got 100. The top score was in the 90s. So, and remember in the upper right, there's the mu. The mu was 65.5, which is pretty bad score on a 100 point test. And the standard deviation was 14.5. So I'm going to give you an example of calculating a z-score on that particular distribution. So let's say you got a friend, you have a smart friend, and that smart friend got a 90 in the face of all this. Well, let's calculate the z-score for 90 on this particular distribution, okay? So here's what we're going to do. Is first, we're going to remind ourselves, you don't have to do this in real life when you're doing it, but I'm just doing this for demonstration purposes, is what our empirical rule stuff look like. Remember at mu plus 1 standard deviation was 80, and mu plus 2 standard deviations was 94.5. So already you know whatever your answer is going to be for 90 is it's going to be between 1 and 2, right? But we just don't know exactly what it's going to be. So I'm just showing you this for demonstration purposes to relate it to the last lecture, but you don't have to do this in real life when you calculate it. Okay, so we know that the z we're going to calculate is going to be somewhere between 1 and 2. And as you'll see on the slide here, I labeled over on the z curve, I labeled where z equals 0, which is the mu, that's 65.5. So we're going to anticipate we're going to get a z-score that's somewhere between 1 and 2. And you'll see in blue I listed the ingredients, right? So we have the smart friend score 90, we have the mu 65.5, and we have the standard deviation 14.5, and then we have our z formula. So let's do it. Okay, so x minus mu is going to be 90, which is our x, minus 65.5. You do that out first, and then you divide it by 14.5, and look, our z-score is 1.69. And that's exactly where we thought it would be. It would be somewhere between 1 and 2. And so as you can see, you can take any x and convert it to z. Here we'll do another example, only this friend is not so smart. This friend actually got a score that was kind of low. It was so low, it was below the mu of 65.5. This poor friend only got a 50. So let's try it again. Let's do a z-score for 50. So again, you know, this is just for demonstration purposes, but remember in empirical rule land, 51 was at mu minus 1 standard deviation. So we're going to expect that between, again, -1 and -2, z is where our 50x is going to land if we calculate the z-score. And so here we are. We calculate the z-score. We have 50 minus 65.5 divided by 14.5, and we get -1.07. And the reason why it's negative is, as you can see, it's on the left of the mu. So then the z-score is going to be negative. And so as you can see, it's exactly where we thought it would be. It would be a little bit to the left of -1. So now we're going to get into something that's a little bit harder, which is the z-score probabilities. You're feeling pretty good about the z-score, but now let's talk about the probabilities. Okay, so remember the probability from the empirical rule? This is just old empirical rule stuff. So remember I gave you a question at the end of that lecture. I said, what is the probability I will select a student with a score between 36.5 and 51? And remember the answer was like this orange area, which is 13.5%. But what if you have z-scores like 1.69, the smart friend, and -1.07, which are the not so smart friend? You know, in other words, you have x's of 90 and 50, which are not on the empirical rule. How do you figure out the percent or the probability? That's the next step with your z-scores. Okay, so now let's ask this question. Let's say, what is the probability that students scored above the smart friend? Now we could also ask for below, but I'm just choosing to ask for above this time. So in other words, what is the area under the curve from z equals 1.69 all the way up? So see, like a little ways through that blue wedge, we wish we knew the area for everything up from 1.69z through the purple area through the little black thing at the top. We wish we knew that area. We only know from the empirical rule what's on the cut points of like 1 and 2, but we don't know this in between things. So how do we figure that out? Well, this is another problem here. What is the probability that students scored below the not so smart friend, right? And in that case, see the diagram, we'd have to figure out what is the part of the orange that that friend gets plus the red and plus a little black part at the bottom. What is the percent or the proportion of the curve that represents that? So that's what we're getting into now. And that's what we do is we look these up in a z-table. So what the z-table is basically they figured out every single z-score you could have between negative 3.49, and I'll go into why negative 3.49, between negative 3.49 and positive 3.49, and they went like every 100th. So they figured out for every single one of those z-scores what the probability is, and they actually fit that all on a table. And so now what I'm going to show you how to do is how to use that table to look up the probabilities. And by the way, if you look up a probability that happens to be on one of those empirical rule cut points, you'll get what the empirical rule says. It's just that the empirical rule is nice because you don't have to pull out the table, but if you have something that's not on the empirical rule cut points, get out your z-table. So how do you use the z-table? Well, the first thing is you want to figure out what area you want, right? So we're going to start and do the not so smart friend because that's a little bit easier actually to demonstrate, okay? So what is the probability that students scored below the not so smart friend? So which is a secret way of saying what is the area under the curve that makes up most of that orange part, all of the red, and the little black part at the bottom? What is that proportion? And so for areas left of a specified z value, you're supposed to use the table directly. So I'm going to show you how to use that table to look up negative 1.07, and then I'm going to come back and tell you what they mean by use it directly. Hi there. So here we are at the z table, and if you have the book, you can look it up in the appendix in on page A8. But there's also a lot of z-tables on the internet. Sometimes they're arranged a little differently, so I'm using this one because it's from the book. So remember the z that we're looking up. We're looking up the z of negative 1.07. So remember how I said they had to somehow calculate all the different probabilities for every single z between negative 3.49 through positive 3.49 every 100th. They had to come up with that. Well, how did they fit it all on the table? Well, this is what they did. See, this is the beginning of the z-table. Remember I said negative 3.49? Well, this is negative 3.4. And then to find the z at negative 3.49, you have to imagine that the 9 is here, but it's going to be the last one here. So see this 9 here? This is what it would be. So just for pretend, if we had a z-score of negative 2.58, I go 2.5 and then I have to go over to the 8 one right here. Okay? Or if I had one that was negative 2.10, right, or negative just plain 2.1, right, then I'd go over just 1 to this 0 line. And see, these little tiny things in here, those are all probabilities. In fact, let's go look up our probability, which is negative 1.07. So we're going to go down here, here we are at negative 1.0, and then we have to go over to the 7 column, right? So what's the 7? Here's the 7. It's 3 from the left. I guess I could have guessed that. So we have negative 1.0987. So this is 0.1423, otherwise known as 14.23%. So that's actually what you get out of the z-table. That's the probability. That's the percent you're looking for. And just in case you're wondering, these aren't all negative. The first page is negative. The second page is positive, is all the positive z-scores all the way up to 3.49. But what I want you to hold in your head is what we just looked up, which was negative 1.07, which is 0.1423. Okay, hold that thought. Okay, here we are back at our slides. And so look at that green part where it says for areas to the left of a specified z-value, which we're doing with the not so smart friend, use the table entry directly. So here was our table entry. It was 0.1423. So we're just going to use that number that we found. And we're going to say the probability then is 14.23%. And that kind of makes logical sense knowing the empirical rule. Now I'm going to show you an example of why I was saying use it directly. In this next example, we're going to look at the smart friend's probability. In fact, we're going to ask what is the probability that the student scored above the smart friend. And the smart friend's at z equals 1.69. So I'm going to demonstrate now for areas to the right of a specified z value. You either look them up in the table, then subtract result from 1, or you use the opposite z, which is in this case would be negative 1.69. And you'll get the same answer whether you do it the first way or the second way, but I'm going to demonstrate both. Okay? So first, I'm going to demonstrate what happens when you look up the probability in the table for that z, and then you subtract that probability from 1. So let's go look up z equals 1.69. All right, here we are back at our z table, only this time we're looking up a positive z, so we don't want this first one, we want the second one. So remember, we're looking up z equals 1.69, so we're looking under here for 1.6, and that's right here. And now we have to go over to the 9 column, so that's going to be 0.9545. So hold that thought, 0.9545. Okay, we're back with our probability that we looked up in the z table. Now remember, we were supposed to look it up in the table and subtract the result from 1, so that's what we're going to do now. So we found 0.9545 in the table. We're going to take 1 minus 0.9545 and we get 0.0455 or 4.55%. This is a little tiny piece, which kind of makes sense because it's right at the top of the distribution, just a little piece of the blue and the purple and then the little black at the top. All right, and so what you want to imagine is that 0.9545, which is like 95.45%, that's the whole piece below z equals 1.69. That's most of the blue, the green, the yellow, the orange, the red, and the little black at the bottom. That's all in the 0.9545. Okay, so again, we were looking up an area to the right of the specified z value, and I showed you the first way of doing it. There's another way of doing it, and that's where you just use the opposite z from the get-go. So we're going to now use the opposite z. We're going to look up negative 1.69. All right, here we are back at the z table, only this time we're looking up negative 1.69. So negative 1.6 is the first thing we need to find in this column. So here we are, negative 1.6, and then we know 9 is the last column. I'm learning that. So we'll go over here. And so that looks familiar, right? 0.0455. Okay, hold that thought. All right, we're back. And so as you know, if you look it up in the table directly, like the 1.69 directly, and you take that probability and you subtract it from 1, which is what we did last, we got the same answer we got now, right? 0.0455 or 4.55%. So it is kind of more efficient to just use the opposite z if you're looking for areas to the right of the specified z value. But I always say when you're done looking it up, compare it to the picture. And I always say draw a picture too. You know, I don't mind if you have normal curves drawn over all of your homework or all over the wall, I guess, or maybe a whiteboard. That's probably more efficient. But it's best to draw it out, label on there where your z and your x are, and then just look at it. Because we know that the little piece above z equals 1.69 is not 95% of that curve. It's just not it. That's over 50%, and we can tell that little tiny piece is under 50%. So If you accidentally do the first way and forget to subtract from 1, maybe if you check it against your normal curve drawing, you'll realize, oh, I made a mistake. So even though there's two different ways to find the probability, if it's to the right of the z value, just try to make sure, no matter which ways you use, that you finally do a reality check against the drawing you make, just to make sure you got the right piece, because there's only two pieces. There's a big piece and a little piece of this curve. And we got 4.55%. We know that's a little piece, and we know from our drawing that we were looking for the little piece. So that's how you do your reality check. Okay, you thought that there weren't any harder questions? Well, here are some harder questions. So this is a little bit more on probabilities in the z-table. So here's another question we haven't handled yet. What if you were looking at a probability between two scores, such as the probability the students will score between 50 and 90? So it's somewhere in the middle, okay? Note that in that case, when you have a between one, you actually have two x's, and we'll label them x1 and x2. So the not so smart friend is going to be x1, and the smarter friend is going to be x2, just to keep these x's straight, okay? So the next step is you're going to calculate z1 and z2, and I'm kind of cheating because we already did these. We already knew the z1 for the not so smart friend was negative 1.07, and we already knew the z2 for the smarter friend was 1.69, so I just put them on the diagram. Okay, and then now here's the beginning of the strategy, and I'll just explain the strategy and then I'll do the strategy. So for z1, you find the probability to the left of the z, so you find the little piece to the left. And remember, you can take the direct probability from the z-table. So that's what direct means, is you just get to copy it directly out of the z-table. Then for z2, you find the probability to the right or above z. So you find the little piece there. And you use one of those two methods I showed you, which we did together. And then finally, imagine like the whole curve. You're subtracting the piece at the bottom, the z1 probability, and you're subtracting the piece at the top. So you're trimming away those two pieces to get the between probability. So that's the strategy, is basically you find out the size, the probability of each of the little pieces on the sides, and you subtract both of those from 1, and that traps whatever's left in the middle. So I'll demonstrate this. So remember, for z1, the probability to the left of z1 was 0.1423. We did that together. And then we used both of those methods, and they got the same answer to find the probability to the right of z2, which was 0.0455. Okay, so that's a little piece at the top, and then we got the little piece at the bottom. And now we'll take 1 minus the piece at the bottom minus the piece at the top, and the total is 0.8122, or 81.22%, which kind of makes sense. It's a big piece in the middle, so it wouldn't be surprising if it was about 80% of the curve. So this is how you do a between one. Here's another question I haven't really handled. What if you're looking at a probability more than 50%? So such as the probability that students will score greater than 50, right? Like the big side. Okay? Well, actually, you just do what you normally would do. You say for areas to the right of the specified z-value, either look up in the table and subtract the result from 1, or use the opposite z, which in this case would be 1.07. So if we did method 1, we'd end up going 1 minus 0.1423, which we already looked up, and we get 0.8577. If we use method 2, we'd take the z of 1.07, not negative 1.07, but 1.07, and we could go look it up in the z table, and we get 0.8577, again, 85.77%. So this isn't actually a harder question. I just wanted to show you how it works when you're getting like a bigger piece, a bigger than 50% piece of the distribution. And here's another sort of similar example where we're looking at the probability that students will score less than 90, okay? So that's easy, right? For the areas to the left of the specified z value, just use the table directly. So when we went and looked up z equals 1.69, we got 0.9545. So that's the answer. It's 95.45% of the curve is below z equals 1.69, or below x equals 90. So, as I mentioned before, but I'll just mention again, you're supposed to treat all probabilities to the left of z equals negative 3.49 as p equals 0. So, I showed you what negative 3.49 looks like in the z table. It's like 0.0002. Well, there's not much smaller than that. So, just if you actually calculate a z and you get like negative 4, just say the p is 0. Okay. Then the second thing is treat all areas or probabilities to the right of z equals 3.49 as p equals 1 or 100%. So as you could imagine, 3.49, that's at the top of the curve. So if you calculate a z and you got like a 5, you can just assume that's 100%, right? Or 1. Okay, so we've gone through how to calculate z, and we've talked about looking up probabilities in the z table, and we've even talked about manipulating those probabilities to get certain probabilities, but we haven't talked about calculating x when z is given. So sometimes you're actually given a z, and you have to calculate the x back from the z. In fact, sometimes it's even harder. Sometimes you're given a probability and the probability is not a z, but you can use the probability. Remember, that's those little percents in the middle of the table. You can go find it in the middle of the table and look up the z that keys to it and then put it into this equation. And so I'm going to just give you examples of some real life questions that you might see, like on a homework or on a test, probably not in real life, that where you need to calculate x and you need to use that formula in the red circle. So let's say I was just bored and I was wondering what is the score, the test score on this distribution that is at z equals 1.5. Okay, so see where z equals 1.5? We never asked that question before. So let's say I just, out of curiosity, wanted to know what would the test score be of a student who was at z equals 1.5. So what I would do is I would take 1.5 times 14.5 because that's what the formula says. It's z times the standard deviation. And then I do that first because of order of operation. And then after doing that, I'd add the mu, which is 65.5, and I get 87.3. So the x, the student who got 87.3, that student got a score that's at z equals 1.5. Now, as you probably imagine, people don't go around asking so much about, well, I wonder what that person's score is at z equals negative 2.3 or whatever. They don't usually phrase it like that. Usually you see more like a question like this, which is, what is the score that marks the top 7% of scores? Now, that's a secret way of saying we are looking for the z at p equals 0.0700. So it's like we turn that 7% backwards into a probability and we say we're actually looking for the z at p equals 0.0700. So how do you do that? Well, I'm going to show you. Okay, so we're on the hunt for probability 0.0700. Okay, so let's start at the top of the table here. You'll see we're digging around in the middle of the table, right? And you'll see like 0.00, that's nowhere near the ballpark because we're looking for 0.0700. So let's scroll up here, or scroll down actually. So now we're in the 0.04 neighborhood. Here's 0.06. Okay, we're getting close. Well, here we have a 0.0708. And that's 0.00008 more than we want it to be. Well, here next door we have 0.0694, and that's only 0.0006 less than we want it to be, right? Because if it had 0.0006 more, it would be 0.0700. So this is technically closer than this one because this is 0.0008 off and this is only off by 0.0006. So we're going to choose 0.0694 as the probability of record for this, for the top 7%. Only we're not going to just choose this. We're going to figure out what is z at that score. So what are we going to do? We're going to map back here negative 1.4 and then we got to go all the way up, which we can guess is 8. So it's negative 1.48. So hold that thought. Okay, we started out looking for the z at p equals 0.0700, but the closest we got was 0.0694, and that mapped to z equals negative 1.48. Now, what I want you to notice is negative 1.48 is actually on the left side of mu. Okay, so that is the z-score at the bottom 7% of the scores. So we're going to use the positive version of that z since we want the top 7%. So we're going to use 1.48, so the opposite z. And now we're going to plug it into the equation. So 1.48 times 14.5, which is the standard deviation, plus 65.5 equals 87. So now 87 is the score that marks the top 7% of the scores. I'm going to do another exercise for you that does this time the bottom 3% of the scores, because this is often kind of challenging for students, so I'll just give you a second demonstration. So as you can imagine, we're going on the hunt now for z at p equals 0.0300. So let's go over to the z table. All right, now we're getting a little good at this, right? So we're digging around in the middle and we're looking for 0.0300, okay? And starting at the top, we're in the 0 department. Oh, here's 0.01 something, 02. Okay, we're getting close to 0.0300. So, oh, here, 0.0301. Could you ask for anything closer? Totally perfect. Okay, so that's what we're going to use for our z, is the z at 0.0301. So let's look up that z. So that z is negative 1.8, and then we look up 8. So it's negative 1.88. Hold that thought. All right, well, we were on the hunt for p equals 0.0300, and we didn't find that, but we did find p equals 0.0301 in the table, and that mapped back to z equals negative 1.88, right? And now we go back to the question, we see that we want the bottom 3%, so we keep the negative. Now, if I'd asked about the top 3%, we'd lose the negative. We'd use 1.88 in the equation. But since we want the bottom 3%, we're going to keep the negative. Okay, so now let's do the equation. So x equals, and then in the parentheses, negative 1.88 times 14.5, which is our standard deviation, then plus our mu, which is 65.5, and the score we get is 38.2. So 38.2 is the score that marks the bottom 3% of scores. And just be happy your score is not in there. Okay, now here's another challenging, hard question. What if the question on the test, or probably not in real life, but on a test, says what scores mark the middle 20% of the data? And so I put little arrows on there just to point out, well, when they say middle, they mean it's hugging the mu. It's actually assuming that there's going to be 10% on the right side of the mu and 10% on the left side of the mu. And so how you start to do this is you figure out the z-score for 1 minus 0.2, which is the 20%, divided by 2, which equals 4, right? So then after that, you know, because 1 minus 0.2 is 0.8, and 0.8 divided by 2 is 0.4. So we get this 0.4. So we go find the z-score at 0.4, which you're good at using the z-table now. So so I'm, you know, looked around and I found 0.4013 in that digging around in the middle of the z-table, and that mapped back to negative z equals negative 0.25, right? And so that is then what I would put on for the lower limit on that one. And then z equals 0.25, the positive version, goes on the other side. So once you've figured out both of the z's, the z on the left and the z on the right, you just have to put them through the equation. So for the left side, we use the negative z, and for the right side, we use the positive z, and that's how we get our limits. So what scores mark the middle 20% of the data? 61.9 and 69.1. Isn't that weird how that worked out? But anyway, 61.9 and 69.1 mark the middle 20% of the data. I totally didn't do that on purpose. It just worked out that way. All right, I can't believe you've made it through all this. I'll bet your brain is ready to explode. So now is a good time to talk about just a little review, just help you come down a little bit from this whole really intense lecture, okay? So first I'm going to do a little Z-score quiz game show style stuff here, right? So if you ever get the question when you're on the test and you're like, oh my gosh, where is X? Where is X? Well, if you can't find X, it's usually in the question. So usually the way these questions go is somebody, like maybe me, will put a mu and a standard deviation at the top of the question. And then there'll be like maybe 5 questions about that pertain to that mu and that standard deviation, but they ask about different x's. And when I would teach this class in person, people would come running up to me in the middle of the test, which you probably shouldn't do. And they would say, "Where's the x? Where's the x? You gave me, these pieces of the equation, but I can't find the x." And I'd be like, "Look in the question. Look in the question." Because I don't want to give it away. And then they'd all run back to their seats and find it. So if you're wondering, you're panicking, where is x? Look in the question. It's usually in the question. Okay, so let's say you find an x, and what do you do with an x? Okay, and you're stuck with an x. Well, usually what you have to do is calculate a z-score. So remember, if you've got an x, you probably have a mu and a standard deviation. You can calculate a z-score out of that. So if you're panicking on a test and you have an x, a mu, standard deviation, just for fun, calculate a z-score and see if it gets you anywhere. Okay, well, let's say you have a z-score. What do you do with a z-score? Well, you always look it up, right? I mean, if you're going this direction, if you started with an X and you get a Z, you got to go to the Z table with it. Okay, so that's your next step. So if you're doing all this work, calculate a Z score, and then you're done, you're like, oh my gosh, what's my next step? Go look at the Z table. Well, what if the question asks for an X, right? Well, remember we have a whole formula for that. So use the X formula. So if there's no X anywhere and it's asking for an X, then use the other formula, use the X formula. And what if the question gives you a P? And I just said P for probability, but it could be a percentage. Like remember the top 7% and the bottom 3%? Well, if they give you a percent, just start digging around in the middle of the Z table. Just start digging around looking for that percent. Because once you start digging around, you realize it maps back to a Z, and then you can get into the groove of using the X formula, and you'll probably get yourself out of this panic. So here are some final tips and tricks for getting z-scores and probabilities right. And I've said this one before, draw a picture. And what do I mean by that? Graph out the question, draw the curve, draw the line for mu, which goes in the middle, and where the x goes, above or below the mu. Just start with that. It doesn't have to be to scale, but mainly you want to get those elements in there. If there's one x, shade the part of the curve wanted, either above the x or below the x. Just color it in so that you get an idea of, do you want the big part, the one that's greater than 50%, or the little part, the one that's less than 50%. If there are two x's, then shade in the area wanted, which is usually in between them. If it's a calculate the x question, put where the z or the p is. So if it was like the top 7%, you could shade in the top little part of the curve. If it was the bottom 3%, you could shade in the bottom little part of the curve. So make this picture and do it at the beginning. Okay? Then note that x is usually in the question. If you can't find x and you're trying to do the z formula and you're saying, okay, I'm trying to make a z-score, that's what it asks for. I'm trying to find a probability, that's what it asks for. Look in the question and you'll probably find the x in there. A big problem that I see is people mistake little z's for p's. Now, obviously, if you've got a z that's like negative, a p can't be negative, a probability can't be negative. So you won't make that mistake, even if it's like negative 0.25, right? You won't make that mistake. And if the z is bigger than 1, you won't make that mistake. So if you see a z equals 2.5, you're like, obviously that's not a probability. But when you have a little baby z-score that's between 0 and 1, like 0.023, it looks a lot like a p, but it's still a z. So a lot of times people get a little lazy, like they hate using the z table, and then they calculate the z-score and it's really little, so they don't look it up. Don't be fooled. You still have to look it up. So if you're calculating z and you get a little baby z like that, it's still a z. Still go look it up, okay? Then finally, remember how step 1 was draw a picture, and I went on and on about that? step 99, or the last step before you're done with the question, is check your logic against that picture. So if you shaded a big part of your picture, your probability should be bigger than zero point 0.5 or 50%. If you shaded a little tiny part of your picture and you're getting like 0.95 something, you know that that's wrong. So please check your logic against the picture before you say that you're done with your question. Okay? So you made it through this long lecture about Z and about probabilities. So I gave you an introduction to the standard normal curve and to those two Z-score formulas. I showed you how to calculate Z-scores and how to look up probabilities. And I also showed you at the end how to calculate X if given a Z-score or a probability. Okay, and all I want to say is, unfortunately, those students, those pretend students on that distribution, none of them got 100%. Okay, that's not the case in our class. A lot of times people get 100% on the quizzes. That's why I can't use your grades as examples. Okay, so good luck on the quiz. Well, hello, it's time for statistics. It's Monika Wahi, your Library College lecturer, back with chapter 7.4 and 7.5, sampling distributions and the central limit theorem. So at the end of this lecture, you should be able to state the statistical notation for parameters and statistics for two measures of variation, name one type of inference and describe it, explain the difference between a frequency distribution and a sampling distribution. Describe the central limit theorem in either words or formulas, and also describe how to calculate the standard error. So here's your introduction to this lecture. And as you can see, I mushed 7.4 and 7.5 together. Again, they felt like a natural fit. First, we're going to review and maybe overview parameters, statistics, and also inferences. We're going to just talk about those ideas because that will sort of ease you into the next part, which is where we start talking about sampling distribution, which is the new concept here. Okay, and then we'll go on to talk about the central limit theorem. And finally, I'll do a little demonstration of how to find probabilities regarding X bar. So if you're not really sure about what that means, don't worry. You should be able to understand it at the end of this lecture. All right, here's the first part. Parameters, statistics, and inferences. And this is the review and overview I promised you. So if you remember from a long time ago, a statistic is a numerical measure describing a sample, and a parameter is a numerical measure describing a population. Remember, SS, sample statistic, PP, population parameter. You probably remember that. Okay, so we have different ways of notating these. So if you look under measure, like you see mean, right? And if it's a statistic, it's X bar. And I say X bar on the slide sometimes because it's hard to make that little line always be positioned above the X. So I'm just lazy. I say X bar. And then under parameter, it's that mu symbol. So it's pronounced mu, but it looks like that thing on the slide. All right, the next two, variance and standard deviation, remember how they're friends? And so the statistic version is the S for variance. It's the S with the little 2 up there, the exponent, because, it's standard deviation to the second is variance, and the square root of variance is a standard deviation. So that's why they have S and then S to the second. For the statistic, okay, for the parameter, it's that lowercase sigma symbol, and it's that to the second when it's variance, and it's just without the exponent when it's just the regular parameter of standard deviation, right? And you're used to seeing these on the slides. This is just review. Also, it mentioned in the book, proportion is p hat, and then the parameter is p. But I don't really go into that. I just wanted to do a little shout out to it. Okay, let's think about the word inference, like infer. Like if somebody implies something, maybe you'll infer it. Like he implied it would be hard if I came over late that night. So I inferred that I shouldn't come over late that night. So like here, you may have heard the term where there's smoke, there's fire. And so you see this on the slide, there's a lot of smoke. Is there fire though? Is that smoke coming from fire? Because if you look at it, it probably could be coming from fire. but there's sort of this outside chance it's not what we think it is. Like maybe, if you've ever used a fire extinguisher, they make all this foam come out. Maybe it's that, or maybe it's like if you've ever had dry ice and then that makes a bunch of smoke, maybe it's not fire, right? So where there's smoke, there's fire. That's an inference. Well, let's see. It's actually fire, right? But we weren't sure. We thought it was likely to be fire, but we weren't sure. And so there's inference is something that you do in statistics because you use probability to make these inference because you can't see the fire, you can just see the smoke and you're not sure, right? So there's three different kinds I'm going to talk about. The first kind is estimation, where we estimate the value of a parameter using a sample. So the sample is kind of like the smoke and the parameter is the fire we can't see. So we estimate it, okay? And we're going to talk about that in chapter 8 more. A second type of inference we do is testing, where we do a test to help us make a decision about a population parameter. In other words, we don't know one, but we want to make a decision about it, so we do a statistical test. And we're not going to get into that. That's in chapter 9. Finally, there's regression, where we make predictions or forecasts about a statistic. That's a third kind of inference, and we actually already did this in chapter 4.2. So the reason why I bring up all of this is that estimation, which is going to be in chapter 8, and testing, which is going to be in chapter 9, but we're not going over chapter 9 in this class. But if we were, you'd have to know this because in this lecture, I'm going to talk about sampling distributions and the central limit theorem, and you need to grasp those things in order to do these two things on the slide that with the box around them, estimation and testing. And so that's why I'm bringing this up now. Okay, so now we're going to move on to talking about sampling distribution and how it's different from a frequency distribution. All right, so let's just remind ourselves what a frequency distribution actually is. Okay, so remember that from a long time ago, what you would have is a quantitative variable. You'd make a frequency table, and then you'd use that to graph the histogram, right? And here I made an example down there of a frequency histogram that shows a normal distribution. And so that's what you would do, step 2 would be you draw it, and then you'd see the shape and figure out what the distribution was of that quantitative variable or that x, okay? Because each one of these is an x, like the middle one, it's almost 30 x's that are in that frequency. Okay, now we're going to talk about sampling distribution. It's a little more complicated. In a sampling distribution, you start out with a population. That's the first thing, is you're dealing with the population. Then you pick an n of a certain size, like you pick a number that you're going to have your sample size be. And then you take as many samples of that size as possible from the population. And then you make an X bar from each of these samples. So there's a ton of samples, right? And I'll show you a little demonstration so you can really wrap your mind around how many different samples that can be. But each one is going to have an X bar, and then you make a histogram of all those X bars. So like I said, I'm going to just kind of show you what I'm talking about. So we're going to imagine this is a population of people. And we're going to imagine we're going to talk about BMI or body mass index, just so you can wrap your mind around this. So you start with this population. Let's decide on an N. How about 5? 5 is good, right? So now what the deal is I'm trying to take as many samples of N as possible from all of these people on the slide. So here's our first sample we took, and we got an X bar for BMI of 23 from these 5 people. Well, let's try these 5 people. Now look, we double dipped with that first one, okay, but we get this X bar of 21. And we can keep going. And actually there's going to be a ton of these, right? There's a ton of different ones. But it's finite. I mean, at the end of the day, there's only so many groups of 5 I can get out of this population on the slide. And each group of 5 is going to have its own X bar. So I could write down every single one of those X bars I get for every single group of 5 I can make out of this. And then I can make a histogram of all the X bars. And Of course, I'd start with a frequency table, but look at the frequencies. They're huge. That's because you can get just a ton of samples out of one population. And so what you'll see is if you make a histogram out of that, it looks normally distributed. It's just that the frequencies are really high because there's a whole bunch of different samples you can take. And remember, this is a frequency histogram of X bars. This is each one of these frequencies is an X bar that you got out of a group of 5 you could take. And so that's what the sampling distribution is. It ends up looking like a histogram, but it's a histogram of all the possible X bars you could get from all the possible samples of whatever n size you picked from the population that you have. So, so this is the fancy way, the official statistical way of saying it, is a sampling distribution is a probability distribution of a sample statistic, in this case X bar, based on all possible simple random samples of the same size from the same population. So that's what makes it a sampling distribution and not a frequency distribution. And so in the next section, so you're probably like, okay, great, that's wonderful, you just explained that. But in the next section, we're going to talk about the central limit theorem. Here comes the theorem, right? And there's a proof for the theorem. And you need to understand this concept of sampling distribution for inference in order to understand this proof. So I just had to go through this. Okay, now we're on to the central limit theorem and how it's used for statistical inference. So I'm going to start by explaining it in words, and see that sampling distributions over there. So this is the words around the central limit theorem. It says for any normal distribution, and remember we're talking about a normal distribution here, the sampling distribution, meaning the distributions of the X bars from all possible samples like we just talked about, is a normal distribution, meaning it's not skewed, it's not bimodal, whatever. It looks kind of like what is on the slide. Okay. And then 2, this is important. The mean of the X bars is actually mu. So I had a student who would say, oh, the X bar of the X bars is mu. And that's actually true. If you actually did the thing I described, which don't try it at home because you'll be up all night taking samples. Okay, but if you did, if you actually got all samples of 5 from a population and got all their X bars and you made a mean of all those X bars, you'd get mu. And how you could check it is, of course, just easily taking a mean of the entire population. Like that would have been the easy way to do it. But no, if you do it this way, where you get every possible X bar for a particular sample size, and then you make an X bar of those X bars, you'll get mu. So that's, it's a proof. So that sounds like a thing that would be in a proof, right? Now here's the next part, 3. The standard deviation of all those X bars is actually the population standard deviation divided by the square root of whatever n you picked. So in other words, if you have the whole population data and you just found out the standard deviation, you just have the standard deviation. But if you did this thing with the X bars, where you took all those X bars and you found the standard deviation of those X bars, that would equal the population standard deviation divided by the square root of whatever n you used to get all those X bars. Again, sounds really proofy and theorem-y, but that's the third part of the central limit theorem in words. And so here's another, some people like to look at it from a formula standpoint. So you'll see on the right side of the slide, in these little formulas, the n means the sample size. And remember, I picked 5. You could pick a different one, right? And mu is the mean of the X distribution, meaning the population mean, right? And then that population standard deviation symbol is the standard deviation of the X distribution, meaning the population standard deviation. So if we look on the left, now this is just a formula version of what I just said. The mu of all the X bars that you could get from a particular sample in a particular population is going to equal the mu of the population. And the standard deviation of all those X bars is going to equal the population standard deviation divided by the square root of whatever n you picked. So now I just want to point out the z thing. We've been doing this z thing, right? But we've been doing it with one x. Now, if you imagine grabbing a bunch of x's, in other words, a sample, this is the formula you're going to be using, which is x bar minus mu over the standard deviation divided by the square root of n, right? And so that's kind of what we're moving into here is what happens if you get a sample and you're looking at x bar, not if you just grab one x and you're looking at that. So I wanted to point out, first of all, that this whole thing is only supposed to happen if your n is greater than 30, okay? Otherwise, you shouldn't really be doing this. Then the second thing I wanted to point out is that this piece underneath and the lower part of the equation, that's called the standard error. They named that piece. And part of the reason why I like that they named that piece separately is I usually make that piece before I even do the equation. So I just have that number sitting around because, there's a square root underneath this standard deviation, and that whole thing is underneath another thing. So it's hard to do all that dividing. So I usually just make the standard error first by taking the standard population standard deviation divided by the square root of n and just have that number, and then later I use it in this z equation. So that's two things I wanted you to notice, so I brought that out on this slide. Okay, here's more on the central limit theorem. So if the distribution of x is normal, then the distribution of x bar is also normal. So if we look at the top, that's an example of just an x distribution. And then if you go do that thing where you take all those samples and you get all those x bars, and then you make the histogram, you'll see the pink one down lower, the x bar distribution. This is just a pictorial example. But even if the distribution of x is not normal, as long as there's more than 30, n is more than 30, the central limit theorem says that the x bar distribution is approximately normal. So remember a lot of that hospital data we've been looking at, like at hospital beds in a state. Often you'll see a skewed distribution. But if you have more than 30 hospitals, then what you could do is you could pick an n and take an n bigger than 30 and take a bunch of samples and get a bunch of x bars, not just a bunch, get all of them, all of the possible ones. And then if you made that x bar distribution, even though the hospital beds would be skewed just as an x distribution, their x bar distribution would be normal. And that's one other important piece of the central limit theorem. That's one important piece of that proof, is that all of those x bars that you get will end up on a normal distribution, even if your underlying distribution is not normal, so long as the n you're picking is greater than 30. And finally, that leads to, how proofs are, they build on each other. That leads to the concept that a sample statistic is considered unbiased, just unbiased, right? It's not perfect, but it's unbiased, if the mean of its sampling distribution equals the parameter being estimated. In other words, the fact that the x bar of the x bars is mu means that an x bar is going to be unbiased. It might not be mu, it might not be exactly the same as the population mean, but it will be unbiased. It's not a biased representative of mu. All right, now let's move on to finding probabilities regarding x bar. So for those of you who want to actually do something and apply something and stop thinking about theory, let's go. Okay, but let's remind ourselves, what are we doing, right? What are we doing? Well, what were we doing? In chapters 7.1 through 7.3, we were looking at having a normally distributed x. So we had this population of quantitative values that were normally distributed. And we had a population mean, a mu, and we had a population standard deviation. And we kept doing these exercises where we were finding the probability of selecting a value from that population, an x from that population, above or below a certain value of x, right? And so we were looking at the probabilities, and we'd look up the z-score and the z-table probabilities. And so basically what we would be doing is converting x to z, right? And we use this formula here to convert x to z. So whenever we had an x, we could put it on the z distribution and we could figure out the probability. So here's what's different now. You'll notice the first thing has not changed. We're still talking about normally distributed x's. We're still talking about a population where we have a mu and a population standard deviation. But now we're not just grabbing one x from that population. We're grabbing a sample. And because we're grabbing a sample, we have to pick an n. So the n's going to be different each time, right? So we're grabbing a sample of the population. Well, how do we boil that down to one number? Well, we're taking the x bar, or the mean value, from that sample. And that's what we're doing the z-score on, is that x bar instead of the x, because we're taking a sample. So when you see the formula below, you'll notice that the other one just had x in it because we only had one. This one has x bar in it because we have a sample. You'll also notice that downstairs, what we had before was the population standard deviation, but now we have the standard error. Remember, I talked about that. The population standard deviation divided by the square root of n. That's where n comes in, because it's going to matter what n you have to make the z come out right. All right, so now that we're reminded of what we're doing, we'll just explain how to do it, right? So let's say you do have an n, right? And you have an x bar, like you grabbed your n and you got an x bar. You can convert the x bar to a z-score using this formula, where of course you have to be told the population mean and the population standard deviation, but then you'll have your x bar and you'll have your n, so you can do the whole equation. And then you'll get a z. And guess what? You do. What do you do with the z? You look it up. So you look up the probability for the z-score in the z table, like in chapters 7.2 and 7.3, only this is just about x bar, basically. So, and then I thought what I would do is walk you through two examples. You're already kind of good at this because this is not too different from 7.2 and 7.3, but I just want to walk you through it because it is a little different when you have a sample versus just 1x, okay? So remember our poor chemistry class that I was in where I got a 73? Well, remember we were assuming it was a 100 student class, so there were 100 students in the class, n equals 100 in the class, capital N, right? Because they're the population. And then if you look on the slide, you'll see the mu of their scores was pretty bad. It was 65.5 on a 100-point test. And the population standard deviation was 14.5. So this was the population of this 100 student class. So I'm going to do some exercises here. Let's say we're going to pick we have to pick an n bigger than 30. So we're going to pick an n of 49, right? Now I'm coming up with a little scenario here. To pass the class, students have to get at least 70, which is a C. So let's pretend this is the question. What is the probability of me selecting a sample of 49 students with an x bar greater than 70? Notice how we ask the question a little bit differently. What's the probability of me getting a set of 49 students such that their x bar is greater than 70? Doesn't that kind of remind you of the central limit theorem, where we had to go back and get like an n of 5? We got different n's of 5s. What's the probability of me getting one of those samples that has an x bar in greater than 70? That's the question, right? And I drew this out here. Remember our old z distribution with also our x distribution, and I kind of drew where 70 is, but I wanted to point out for you the probability for an x bar is going to be smaller than for x, because you're going to have to do a lot of work to get that x bar to be above 70, right? So here we go. So I'm just going to remind you that the equation at the top and the equation at the bottom are the same equation. I'm just using the term SE for the standard error. And I like to calculate that separately, like I told you. So I like to do that first. So we're going to do that. And how do we do that? Well, the n was 49, right? And the population standard deviation is 14.5. So that's where we get this number, the standard error of 2.1. So now let's calculate z. All right, here's z. So z is our x, which is our x bar, which is 70, minus 65.5, which is our mu, divided by our prep cooked standard error, which is 2.1. And we get a z of 2.17. So we're tempted to look that up, but let's look at our picture. So here's our z distribution. And what we're going for is this little piece at the top, right above 2.17. So that's a little piece. So we got to look for that, right? Let's go look. Um, so because we're going to go for the piece at the top, we're going to use the opposite z. There's, remember, two ways of doing this, but everybody seems to prefer the way where you use the opposite z if you're looking for something to the right. So we're going to use negative 2.17 to get the little piece, right? Because when you look that up, I'm not going to demonstrate. You guys are good at this now. You get p equals 0.0150. Um, if you were to look up 2.17, then you'd get the big piece. So that's why we do this. And so then the answer is, remember the question was, what is the probability of me selecting a sample or a set of 49 students with an X bar that's greater than 70? And remember how this test really sucked. I mean, the mu was 65.5, so it was pretty hard to get a high score. So the probability was pretty low. It's 0.0150, or if you do the percent version, 1.5%. Okay, now we're going to try a different one. That one was asking, what is the probability of me selecting a sample with an X bar greater than a certain number? Now we're going to talk about the probability of selecting a sample with the X bar between two numbers, right? So again, we're back with our poor student class that with this terrible chemistry test. This time I decided to choose the n of 36. You'll notice that I always choose perfect squares for n's because you have to take the square root, and I'm just lazy. So, okay, here's our question. What is the probability of me selecting a sample of 36 students with an X bar between 60 and 65? And just, I drew this picture up here to remind you that that's going to be on the left side of mu. You know, we're going to be dealing with negative z's, right? And so we have two. Remember when we would have two x's back in 7.2 and 7.3? Well, this is now a situation where we have two x bars. So you just got to name them x bar 1 and x bar 2. And again, I show you this demonstration, you know, these red arrows, but the probability for x bar will be smaller than for x because it's harder to get a whole group of people together to give you an x bar in between a certain place. All right, so this is not new. These are the same formulas I showed you before. I just want to emphasize that making your standard error first can really help you as you move along through these problems. It just makes it a little easier to calculate, especially in this case where we're going to use the standard error twice. So again, what we do is we take, this would look exactly like the last standard error, but it's different because our n is different. So this time our standard error comes out as 2.4. And what I just want to remind you is that the more n you get, the bigger that square root of n gets. I mean, n gets bigger, the square root of n gets bigger. And then the smaller the standard error gets. So you can make the standard error really small if you just get a lot of n, right? So here's Z1 and Z2. I put them both up there, but we can just walk through this. You know, X bar 1 is 60 and X bar 2 is 65 because it's between 60 and 65. So you see that, you see what's going on in the slide. And like I told you, you know, both of these X bars are below the mu, so they're both going to have negative Z's, and so we've got our negative Z's. And now we have to just remind ourselves, well, what are we doing, right? And so, you see Z1 is at negative 2.28. So that's our little piece at the bottom we're going to want to trim off. And then the big piece at the top for Z2, that starts at negative 0.21. So that's just, remember the picture is really helpful. So now we're going to go deal with the probabilities, right? So for Z1, we're looking at something to the left. So we just leave the Z alone and go look it up. And that's P equals 0.0113. For Z2, we got to flip the sign because we have to use the opposite Z because we're going for the right. So that was the probability 2. And we can check that, see, because we can see that's more than 50% of that shape. So it's 0.5832. Okay, so we got our probabilities now. And just like last time, we got to take 1 minus both of those pieces, right? And then we get the probability in the middle, and that's the probability of drawing a sample of 36 students with an X bar between 60 and 65. And just to translate that to you, the answer, the probability is 0.4055, or if you rounded it, and you like percents, you could say 41%. So, in conclusion, we reviewed the parameters and the statistics and those notations, and we talked about inferences and what we're doing with inference. Next, we talked about what a sampling distribution is and how that's different from a frequency distribution, so you can tell, what's going on with that. Then I presented to you the central limit theorem, which may have been kind of confusing because, theorems always are. They're always about different principles and about different things equaling each other. But because of the central limit theorem, we then have permission to do the operations we're doing after that, which is finding probabilities regarding x bar. The central limit theorem says that, this is how the world works, so you get to use the standard error and you get to do these kind of calculations. So now you know how to, in addition to finding probabilities regarding x, you can find probabilities regarding x bar. Don't you feel smart?